And it starts with this notion that energy is everywhere. So not only is matter itself energy, there is energy all around us that is not formed as matter. And you could say that there is energy in space. And in fact, there is lots of energy in space. Both relativity theory, which is the theory of gravity for the most part, the special theory of relativity focused on electromagnetism, the general theory of relativity focused on gravity, and quantum physics is almost purely about energy. And I'll get into this deeper and deeper. But both of them require that there be, you can think of it as free energy, vacuum energy, energy in space. But for their equations to work, they both need this energy. Now, they really disagree on how much energy. And this is one of the reasons why you've probably heard this before, that the equations of relativity and the equations of quantum physics just don't match up. If you try to use relativity's equations to describe the behavior inside an atom, it just breaks down. If you try to use quantum physics equations to determine what would happen in a black hole, it breaks down. So you've got the really large and the really small, and they don't seem to be able to meet. And one of the big differences is this assumption of how much energy there is floating around available. So with relativity, it needs what's called the constant, the cosmological constant, and more modernly, dark energy. So back when Einstein was first presenting the general theory of relativity, he had to come up with an arbitrary number or an arbitrary quantity of energy that existed in space. Because otherwise, even though his equations were elegant and self-integrated, they didn't match the reality of the behavior in astrophysics. So he was forced in a way to say, well, there must be X amount of background energy always present. When he put that in, his equations matched up perfectly with observed behavior. So they could predict the motion of the stars and the planets and the other galaxies, and it all just worked really neatly. But one of the things that he had to do in order to come up with his number that he just kind of pulled out of the ether was that he had to decide that the universe is static, that it's neither expanding nor contracting. And it was not long after he published the general theory of relativity that Hubble discovered that, in fact, the universe is expanding. And this was why, for those of you who know some of this lore, Einstein said that the cosmological constant was his greatest blunder. Because it wasn't tied to anything. It wasn't based on anything except this assumption, which turned out to be completely wrong, that the universe is static. So now we know the universe is expanding, and they factored in this knowledge, and they increased the amount of energy that they put into the cosmological constant. Well, then, in the latter part of the 20th century, they discovered that not only is the universe expanding, it's expanding in an accelerating rate. So the rate at which the universe is expanding today is slightly less than what it's going to be tomorrow. So things are not only expanding away from us, they're expanding away from us faster and faster and faster. This really blew everybody's mind, and this is why we have conceptions like dark energy. So back in the day, to steal Oldsmobile's slogan, back in your father's day, the universe was not only static or expanding at a very modest rate, the majority of what they were